Okay, so this is the recording for 10.9. Um, we're going to talk about file system I/O. If you look at the syllabus, which of course I don't have readily available, I did 5 seconds ago. This is going to be mostly a presentation. We'll do the demo in class. This is actually relatively simple, so there's not a lot to this, but this is the first area where we're going to get uh, system oriented. Um, I'm sorry, I can't think of the word. System oriented structs. We're going to deal with file metadata for the first time. We're going to deal with stat. We're going to deal with those type of things. We're going to deal with permissions. We're going to deal with ownership. Not really. We talk about permissions at this point, but we don't do much with them. We're mostly talking about having to look at it. We're going to discuss directory, including entries, creation, removal, opening directory streams, and reading directories. How do we move around the file system is the basic idea. And this is also the place where we discuss links, symbolic links, and those type of things. We'll discuss copying and moving files. It's not as exciting as you hope. Uh, Copying and moving files is simply a matter of, um, I'm trying to think of the word. It's simply a matter of can't think of it. I'm sorry. Brain farting. It's simply a matter of, copying a file is simply a matter of, open the file, saving it somewhere else. Moving it is a little bit of a different animal, but we'll talk about that as well. I think we'll have examples, but it's really more file I/O than file system I/O. So it's pretty simple. Other high-level languages have high-level architecture for dealing with these. We do not. Also, be aware, some of you may not be using Linux, not be using the Debian file system. You're going to start to encounter pretty quickly situations where the Linux file system is different. And so just be aware. Um, we use a reference file system so that you can use ours. Any attempt to use a Windows or other system will just result in a lower grade. So make sure you're aware of that. This is definitely going to be different here. So if you've been using some alternative mechanism, these are going to be different pretty quickly. One of the differences we encounter when we deal with different versions of Linux, of course, is we start to encounter file system differences. I'm not here for those. That's why we have a reference system. Okay. In order to simplify our discussion, not to have to talk about thousands of file system calls and how they work, we're going to keep it relatively simple. Okay. So we're going to discuss copying and moving files as well, but don't expect much there. It's just some standard operation that we do. Files in the metadata. Each file is referenced by an inode, which is referenced by inode number. Every file in the file system has a inode. Okay. The inode is both a physical object located on the disk and a logical entity complete with the data structure in the kernel. The inode essentially stores the metadata associated with the file, and you can type this inode by using the iflag with the ls command. It's very, very simple. Okay. However, just be aware that we're going to talk about this in detail, but we actually have to get the information from a number of places. So it's not necessarily super easy. So we'll talk about that as we go along. The Unix provides a family function to obtain the metadata. Stat, right? Stat is the most common one. We're going to deal with a struct stat, and we're going to give it a buffer. You're going to create a variable, and you're going to pass in a pointer to that struct. Fstat's the same basic idea, except you're using a file descriptor rather than a file name. Lstat is for links, so we're going to generally avoid that, but that's what that's for. Okay, this is what a stat looks like, and it basically holds the information within an inode. This is the basic information that we have when we deal with inodes. So we have a device ID containing file. It's usually a number. We don't want to really get into what it is and so forth. You'll see some examples of me playing around with this when we do the demo. Inode number is an inode. Again, it's a number. Mode are the permissions associated with it. Remember, the ST mode is not going to look like an obvious number. You actually have to do something to break it apart. And we'll see. Hopefully, we'll have time to do that. The number of hard links is given by ST in link. Then we have the user ID, the group ID, and the device ID, right? The device ID is for special files. We don't really care about that. Um, I don't think at any point do we care about that. But the ST size shows the size in bytes of the file. Block size shows the block size for the file system. Note these are not always the same. Oh, no, excuse me. Block size is literally the same for the different file system. Remember, you can have Linux be connected to, you can have 3 or 4 hard drives in the same virtual file system. So this is not necessarily uniform across the entire system. Um, but the number of blocks, remember, is not necessarily a block size times the number of blocks equals the total size in bytes. That's not necessarily the case. Remember, a file can occupy part of a block. Just be aware. Then we have some times, A time, M time, and C time. Status change is the last time something was changed on the stat. This is actually really useful to remember. A time is the last time it was accessed. Last time the bytes were accessed, not the stat file, but the last time it was accessed. The status change could be anything. You add a hard link, you change the permissions. You may not modify the file at all, but you may modify any part of the struct stat. Your user ID is an example. Anything of that would change the C time, the status change time. And of course, last modification time. This implies that you've modified not only access to data, you've actually modified it. So here's a stat example. We're going to get a struct stat SB, and we're going to have a return. If argc is less than 2, we're going to have an error. We're going to ignore that. But we're going to call the stat function. It's in sysstat. We're going to go and grab it. That's the name of the file that we're grabbing. If return is 0, it's an error. Or excuse me, if return is non-zero, it's an error. Otherwise, we're going to print F. And it's going to be S is LD bytes, right? So argv is going to be the file name, and we're going to just print the size, right? We're going to play with these and just print the size. And we're going to play with those various fields of this. And when I do our example, it's going to look like that. Okay, here's another example where I print the file type, and now we have to do something, right? So now we're going to do st mode and sifmt. So we can grab that, and if we do a case statement, we can actually determine if it's a character device node, a block device node, a directory, FIFO, which is a pipe, a symbolic link, a regular file, a socket, or I don't know what it is, right? But that's all coming from st mode, okay? In st mode, it actually has a file format associated with it, right? So we can actually grab out what kind of file it is. Actually pretty cool, right? It's not that cool, but it's pretty darn useful. Stat can also be used to upturn the permissions with 2 others to set this. So we don't usually set it via modifying things. We go get it. But when we go to set those values, we might use chmod, which takes a character path along with the mode. Again, you remember my setting this up via a create method in class, my demo on 10.7. We would do it the same way. We would just set the mode operations along those paths. It is relatively easy to do. We just have to remember the various things. And that list is actually in your book, so it's there. fchmod does the same thing. It just uses the file descriptor. Ownership. In stat, the ST, UID, and GID fields provides a file owner group. We can set them using the following. So the Unix command for this is chown. And so, of course, we can change the name of a to file owner group by doing so. Note that we have to have permission in order to do that. I have to own it in order to change the ownership. So if I wish to change the ownership from Bob to Alice, if I'm Bob, that works out. If I'm Alice, I can't take away ownership from Bob without permission, right? If I'm root, I can do whatever I want. But that's the basic idea. So we don't use this that often, but you can actually use that information. Now, couple things. We haven't gotten into user things yet because we haven't. When we get into processes, which is literally the next week, we'll get into, or I believe it starts don't remember. I'm sorry. I'm going to open up the actual syllabus just as a reminder. Um, yeah. So it starts next week and it ends on 10/21. It's file process and management. In those in that class, in those classes, we'll actually be able to go get the owner name instead of just the user account name, instead of just having the user ID, right? As an example, we're going to be able to set it, go get the username, and then go get the GID or given the GID or the user UID, we're going to be able to go get the username or the group name and vice versa, of course. We'll see how to do that in next class. In Unix, a directory is a simple file consisting of a list of directory entries. Each entry is an inode name mapping, aka link. This is what a link is. When you think about what a hard link is or what a soft link is, essentially a link is an inode that maps to some other thing. Okay. Now, what does that mean? That usually means it maps to a name. Okay. Every directory contains two special directories. Dot is right here. Dot dot is the parent, except for the root directory, which dot dot is also right here. You don't need to remember. Well, you should remember that actually. That's actually important. It does actually translate to right here. The parent of root is in fact the root directory. So every process has a current working directory. So if you open a file, you do something in the file, you do something with a file, whatever, it's going to try to do it in the current working directory. It's a starting point for resolving relative path names, and the process can obtain and change its current working directory. We just use get current working directory, takes this character buffer and a size, change directory, takes a path, and it changes it. We often get it so we can return to it later. So, and you go, wait, what? So we usually go get the current working directory, we change the working directory, and then we come back, is usually the case. So we might use the file descriptor as it could be more descriptive, could be more efficient, but it's not necessary. Okay, we can do it either way. But like I said, we typically do get the current working directory in order to change it and then in order to come back. That's the most common use of current working directory. Oh, one other thing I want to talk about directories. So remember, a directory is just a list of directory entries. It has an inode and a name, 100% of what it does. So when we go to create a directory, you can do make directory. I'm sorry, it takes a path and a mode. Just be aware that the permissions are taking the mode plus the UMask and O177. It doesn't work exactly like you expect it to, but we'll see some examples of that so you get a feel for how it works. It's actually relatively simple. Don't overthink it. It's actually fairly simple. Removing directories, you can type rmdir. There is no recursive directory. If the directory contains things, it does not work. You're like, wait, what? Yeah, so there's no recursive directory. You have to go into the directory, remove the things, go in, and so forth. It's not as trivial as it looks, but it does in fact have an RM directory. You can delete the path, but it doesn't have a recursive version. So if that path has something in it, it doesn't work. Reading directory's contents, we can read a directory. Now note, it takes a directory pointer, open directory, just like a file. This is why I spend so much time talking about what a directory is. This is why. And you go, what do you mean? So when you go to read a directory, you're not thrown off by the fact that you have directory entries. Okay? That's what it is. That is the file pointer, and it is a set of, excuse me, the directory pointer is literally just a set of directory entries. Okay, so you give it the path name and you get a pointer to direct a series of directory entries or directory stream. Directory stream is basically a file descriptor with some metadata. We can obtain the file descriptor if we want, or FD, same thing, what have you. But I'm sorry. So we read from the directory's contents by using struct direct pointer read directory. And so what this does is it reads the directory given by the pointer to the directory and returns a direct. What is a directory entry? You might ask. It's an inode number It's an offset to the next direct. We don't care what that is. That's used internally. And then you have the length of the record, and then you have the type of file. Again, we don't care about reclen. We don't do anything with it. So the length of the record helps identify where the next direct is. It's used in the read directory process. We don't care. We do care about the DNAME. Why? Because if I wanted to open the file and do something with the file, I would need the DNAME to get it. Okay. And of course, dtype. What if dtype is a file? Great, we do something with the file. What if it's a directory? We might want to recurse into that directory. Remember, we're going to use recursion heavily in this section, or we didn't say it, but we're going to use recursion heavily in this section simply because you are in fact dealing with directories which can hold other directories. It's just hard to get around it otherwise. Now, we close the directory stream. It's like closing a file. We close it. Nothing special here. A link is essentially a name for an inode. We can create more than one link. I'm going very fast. Unfortunately, I apologize. I get it. I'm sorry. I am going very fast. I don't know why I'm going this fast, but it's usually what happens with recordings. But anyway, a link is essentially a name for an inode. We can create more than one link to the same inode, only on the same file system. We call those hard links. Another type of link that's not a file system mapping, but a higher level pointer is interpreted at runtime. These are symbolic links. You go, wait, what? So this is the closest thing you have in Windows. So you can create a shortcut which actually points to another file or points to a directory. Pretty simple, right? That's what a link is. Can be relative or absolute. It may point to non-existent files because it's determined at runtime. We refer to those as dangling symlinks. But that is what a symlink is, right? A hard link is literally another name for the same inode, right? Whereas the symbolic links are interpreted at runtime. When you actually go to do something with the link, we determine what it is. Okay. Hard link, you can create those with link. We don't do anything in this class except avoid them. And then you create a symlink. Same basic premise. You can unlink a symlink or remove a symlink as well. Now, what happens when I remove the last link to a file? Yes, I'm deleting the file. Literally, you can delete the file using the remove process. It will, in fact, remove the file. We'll have an example later on. Anyway, copying and moving files. There's no system call for copying a file. We just open the old file, open the new file, copy them. Ta-da! Pretty simple. But for move, there is actually a system call. We can actually rename a file by using old and new, and it automatically renames it if it is possible to do that. Okay, so that is our file system I/O, including file system metadata, stat, permissions, and ownership. We discussed directory manipulation, including entries, creation, removal, opening directory streams, and reading directories. Note, I'm going to do some of the stat stuff today. I'm not going to do all of it, obviously, but I'm going to do some of the stat stuff today. And we're going to come back to directory manipulation as well as doing something with files as a result of that directory manipulation next week. But we talked about links, including hard links and symbolic links. Remember, we can actually delete a file by removing a link, right? We can remove a link. If it's the last known link to a file to an inode, it's the last name to inode mapping, it deletes it. Cha-ching, which is awesome. So we'll see that example. I don't know if I'll do that today. I may, because I may just do some really simple looping through a directory stream just to show you that, depending on time. But renaming a file is also something you can do as well. Note, when we're renaming, we have to remember that you're actually opening the file. Can you think of it as opening the file and saving it, right? That's not at all what's happening, right? An inode simply is just changing the name for the inode. There's nothing actually happening besides that. One of the things we're also going to talk about, and we haven't done it yet, is are we talking about full pass, partial pass, and so forth? We'll talk about that in a lot more detail as we go along as well doing the demo. Note that I'm going to demo some like broad stroke stuff today. I'm going to do some really simple like overview stuff, like looking at stat and printing stuff out from stat. looking at the inode data. But what I want to talk about more is manipulating directory streams and manipulating files next class. What I'm mostly going to do if I have time is I might read a directory and print out, say, file names, right? Or play with removing a file or play with renaming a file. I doubt I'll do either, but it's possible that I could. But like I said, I want to show you a couple things, but I want to leave most of that manipulating the file system, moving around a file system for later in time, because it's not trivial and it's important that you get it right when you in fact do it. Okay. So we talked about file system I/O, including file data, stat, permissions, and ownership. We discussed directories, including entries, creation, removal, opening directory streams, and so forth. What I really want to make sure that we do later is reading directories and manipulating the directory structure. I may show you how to make a directory. I may show you how to do this, I may show you how to do that. But the goal of today will not be doing anything complicated with directories or subdirectories. We explain links, including hard links and symbolic links and their system calls. There's really nothing to that. The real reason we talk about it, because we don't really want to play with links, sim links or regular links. We don't really want to create them. We want to show you remove. And why do I want to show you remove? Remove actually removes a file, right? It actually removes a file. It can delete a file just by changing making the path to the inode go away. If that's the last, if you remember I talked about it, but I didn't go into any detail. Oh, come on. The number of links, if it's the last hard link to a file and you delete it, it goes away. It deletes the inode, deletes the actual file. Which is pretty awesome. We'll see that in a second. We'll see that in a little bit. Copying and moving files, we don't really do that, but I might show you a quick, simple example. Almost everything we're going to do is going to be within the directory today. Why? Because the recursive nature of directories involves a lot of pointer manipulation and a lot of knowing what the hell I'm doing as I'm doing it. And so it's not trivial. Okay, so it's very much a holy crap, what's happening type thing. So we need to make sure that we're doing it correctly. Especially with a lot of pointer manipulation involved, we want to make sure, and recursion functions, we want to make sure that we're not overwriting things we shouldn't be overwriting. Okay. We'll talk about that in more detail as we go along. Again, if you have any questions, today is supposed to be 10/9. The recording is 10/9. I'm actually recording on 10/3. But if you have any questions, I am probably back in town by the time you see this email, but I will not necessarily be able to come to class. So if you have questions, make sure you ask them. But I expect to see you all bright-eyed and bushy-tailed on 11/11 when I return, which is the week after. No, excuse me, not 11/11, 10/14. Okay. But like I said, if you have any questions, make sure you ask them. I don't believe, if I'm looking at the homework correctly, you get a homework until next week. So more power to you. No, it says you get a homework on 10/9. So you are going to get a homework today. I'm sorry, I did say that wrong. You are going to get a homework on 10/9, but it won't be due until 10/16. I will do some of the demo stuff, but you might learn some of the stuff that you need to do on 10/14. Like I said, if you have any questions, please make sure you ask them. Thank you so much. All right, have a great day and look out for the demo later.